Hey, everybody. So I want to kind of not take a little detour, but we're going to approach a couple of the problems we've been looking at in a little bit different way, maybe. And this is a little more just, I guess, less practical information at this moment, but just some stuff to chew over a little bit. So here's something related to the idea of the tangent plane and our partial derivatives that I want to get at. Remember, one of the ways in which we defined the tangent plane had to do with, or one of the conditions was that the partial x and y derivatives existed and were continuous. So I want to look at why that is important, okay? And we're also going to get at the notion of differentiability. So let's actually start there with a little thought to differentiability for functions of one variable, right? So we usually say something is differentiable if, you know, something along the lines of if this limit exists, right? So our definition of a derivative, if this thing exists at a point, then we'll say it's differentiable there. And that's a good enough definition because when that limit exists, pretend I actually hit here, right? It means we can have a tangent line. It's really a way of saying this curve, if you look closely here, is well approximated by this tangent line, right? And when we have things like, you know, a corner, like an absolute value function, there's no good approximation to these corners, right? And we saw in Calc 1 or whatever class you first learned about derivatives in, that this limit breaks down when you have these kinds of situations, right? The situation is not quite as easy when we have functions of several variables. So we're going to look at a particular function and see some of what can happen here. So let's begin with the function. So I'm going to define a function for you here. This is a fairly classic example of this thing breaking down, this stuff breaking down. So this is going to be a little piecewise function. xy over x squared plus y squared if we're not evaluating at the point 0, 0. And the function is equal to 0 if xy is the point 0, 0. Okay. So first thing, I want to show you that the x and y derivatives exist. And so to do this, I actually have to go back to the derivative, the definition of the derivative. I can't use some of our tricks. I'm going to have to actually use the definition. So for instance, the definition of the derivative at 0, 0, right? So this is where I'm looking at the point 0, 0. What we're going to find is that these derivatives exist, but there's no good tangent plane here. And so this thing isn't actually going to be differentiable. So there's kind of a lot of ideas to play with. So let's take the derivative. It's the limit as h goes to 0 of f of 0 plus h comma 0 minus f of 0, 0 all over h. This is going to be the limit as h goes to 0. So now I'm plugging in 0 plus h, or just h, into the function. So remember here, this part of the definition, we refer to xy over x squared plus y squared. That's because we're not at 0, 0. H is non-zero, so we're not at the point 0, 0. So I'm putting h into this equation for x, and I end up with h times 0 over h squared plus 0 squared minus f of 0, 0, that's just 0, all over h. And this is the limit as h goes to 0. Well, this is a 0. 0 minus 0 is 0 over h. And this is just 0, right? Because we can do the algebra in here first. 0 over h is 0, and the limit of 0 is just 0. Okay? So, a similar thing happens. In fact, I'm not even going to write it out. It's pretty obvious the exact same thing is going to happen. Notice this function is symmetric in x and y, meaning they both do exactly the same things. So I'm just switching where that h shows up, and it works out precisely the same. So at this point, the derivatives both exist, okay? But they are not, but this function doesn't have a tangent plane here, okay? So let's think about what it would mean if it did. According to our tangent plane formula, the tangent plane would be given by z equals, we would take the x derivative, which is 0, times x minus 0, plus the y derivative, which is 0, times y minus 0, plus the value of the function at 0, 0, which is just 0. In other words, the tangent approximation, if it exists, and it doesn't, but I'm pretending like it does for a moment to show you one of the problems with this, is the tangent plane approximation is just the xy plane, right? So what would that mean is any tangent approximation near any linearization, linear approximation, or tangent plane approximation near the point 0, 0 is just 0, right? Now that can be fine, right? For instance, if I have something like this, if I have some kind of maybe the bottom of a sphere or a paraboloid that hits the x, y axis right at the origin, here's the z axis coming up, so this is like, right, the bottom of some ball, right? But the xy plane, this tangent plane at the bottom, might be the best approximation, and it's a pretty good one. If you're close to the point of contact, right, that's going to be not very, right, let's just draw the perspective from the side. If you're close to that point of contact, as you move away from the point of contact, you're not very far away from 0, okay? However, something very different happens with this function, okay? We're going to look at a graph in a moment, but this is a tricky graph to look at. So we're going to start with some algebra. So for instance, let's imagine, right, so here's, let me try to draw this in a way that will be helpful, I hope. Here's the xy plane. Now, my surface, whatever it looks like, right, so here's just some surface floating over the xy plane. Actually, we know that its value at 0 is 0, right? So if this is going to have a tangent approximation, we hope that the function is near 0 there, right? So maybe it's curving down in some of these places. It's hard to draw like a little pit or something like that touches 0 there, right? That would mean there's a good approximation there if the nearby values are close to 0. Let's test what some of the nearby values are. For instance, if this is the x-axis and this is the y-axis, the positive x, positive y, what if we were to put in values for our function along the line, right? So this green line, imagine this being a green line living in the xy plane. And this is the line where all the points on this have the same x and y coordinates, okay? So if we put points along this line into our function, right? If every point in that line has the same x and y coordinate, in other words, x equals y, and remember, I'm not looking at the point 0, 0, I'm looking as I get closer to 0, 0. So I'm looking at points like 7, 7, 3, 3, 1, 1, 1 half, 1 half, 1/3, 1/3, 1/10, 1/10, 1 1/1000th, 1 1/1000th, right? I'm looking at these points approaching that point from one direction. This function becomes, because x equals y, x squared over x squared plus x squared, or x squared over 2x squared, or 1/2, right? Everywhere along that line, the value of the function is 1/2. Let's do another one. Now I'll try to, let's look at a different line. Let's look along the line, for instance, x equals negative y. Okay, now they're opposite. Well, what's going to happen? In the numerator, they're opposite, so we're going to get, one of them is going to be positive, and I'm only drawing the lines on one side. You can continue this pink line through and do the same thing on the other side, or the same goes for the green line. It continues through onto both sides. I just drew one place. You're going to get negative x squared in the numerator and 2x squared in the denominator, right? Because you're plugging in a negative x for y, but squaring it in the bottom, so it becomes positive, but at the top it doesn't get squared, so you keep the negative. You get values of negative 1/2. Okay? Let's just do one more of these. Let's look along a different approach line. Let's try approaching along the line, something like y equals 2x. I think I drew that correctly. I'm trying to reverse the normal way we draw these graphs. So if y equals 2x, then in the numerator we get 2xy. In the denominator we get x squared plus 4x squared. Oops, sorry, this should be 2x squared in the numerator because I'm putting in 2x for y, which turns out to be, we got 2x squared over 5x squared is equal to 2/5. Right? So let's try to put together these ideas. What I'm saying is, if here's my origin, right? Imagine being a little point, right? A little ant at this point. This function is an impossible hill because, right? Think about what we mean by an approximation. When we approximate something, right? If I'm approximating this curve right here with the tangent line like this, if I move from this point, my curve only moves very gradually away from that value. But in this function, if I move off this point, any tiny increment, I immediately jump from 0. Right? I guess that's not true in the directions along the axes. Along each of the axes, you're going to jump to, you stay at 0 because the numerator is always 0. But in any other direction that's not along one of these axes, I immediately jump to some other value. For instance, if I move in the direction of this green line, right? So let's say that's in this direction, my function goes from 0 immediately up to 1/2. But if I move in a different direction, like y equals 2x, my function jumps to 2/5. And if I move in a different direction, so I'm standing at the bottom of this hill, and at each direction, it jumps to a different height immediately. So I've got this infinitely steep cliff in all directions, but the height of the cliff changes in every direction. Okay, how do you make a good approximation there? Right, the approximation, the tangent plane approximation, just says the value barely changes. Right, that's what a z equals 0 approximation is saying. Is if you move, it acts almost like the flat function that never goes above 0. But that's not the case at all, because in every direction, we jump to different values, right? And we jump or descend, right? Going down to negative 1/2 in some direction. So there's no good approximation here, right? There's no way to make sense of this shape. In the same way, when you have corners, what's a good approximation, right? You might say this one, but there's no, it doesn't really look like that shape. That's a better way to say it, right? That straight line in no way looks like that corner there. And the same thing happens here, but it's much harder to look at and think about. Okay, let's take a look at the graph for a minute and then come back to a couple of other ideas. So let's see. Let me share again. There it is. All right. So here's the graph of this function. Right? It looks pretty flat from here, but there is some stuff happening in the center there. Let's extend. Let's zoom in on the z coordinate, make that axis jump a little bit. And you can even see the computer having some trouble rendering it there, right? These little spikes and stuff are not actually features of this graph. They're features of the way this computer is trying to graph it, right? You often see this when you have functions that have that functions that we might say misbehave. They're very erratic, and the computer is just computing various points, and it doesn't always know how to connect them if a function's doing kind of crazy things. So notice what happens as we get close to the origin, right? You can kind of see what's happening with this shape. Over the origin is right there in the middle, of course, and there's these like pits on one side. There's this ridge up here on the other side. Here's the plane y equals x. Remember, we talked about approaching, right? This is what I was getting at was if you approach that 0, 0 along this line, right? The values of the function are just at 1/2. You can see it here, right? That increase our view. So you can see right at 1/2. Again, these jagged edges are not really what's going on with the function. The computer's just having a tricky time making sense of all this. Maybe if I zoom out a little bit, it will never quite get it right. But you get a good sense, right? It's equal to this value everywhere. On the other hand, if we go along the line y equals -x, the intersection is now below by 1/2 a unit, right? So at every point except the origin, and then at the origin it jumps to 0, right? And then we looked at one other line, y equals 2x, and you can see this intersection right at 2/5 or 0.4. You can kind of see it behind. It's happening underneath the intersection over there. And so this behavior of jumping to all these different values from the origin makes having a tangent approximation impossible. Okay. All right, let's do something else with this function. Let's see what went wrong, or one way to think about what went wrong. So let's look at these derivatives again. So I'm going to actually erase this and just rewrite the parts that are relevant. So what we did was we discovered that the derivative with respect to x at the origin is 0, as was the derivative with respect to y at the origin was equal to 0. Okay. Let's look at the derivatives everywhere else. Okay. So now I'm just going to take derivatives in the way we have been, partial derivatives. Let's look at df dx. I have to take a quotient rule. The derivative of the top is just y times the derivative times the bottom, minus the derivative of the bottom with respect to x gives me 2x times the top. So I get squared y all over x squared plus y squared, which can be simplified to equal, we're going to have y cubed minus x squared y over x squared plus y squared squared. And df dx is equal to, df dy is going to be equal to something very similar. So again, I'm going to use the fact that x and y are symmetric here, meaning they do the same things as each other. And so when I take the derivative with respect to y, I'm obeying all the same rules, just switching the symbols x and y. And so what I'm going to end up with is x cubed minus y squared x all over x squared plus y squared squared. Okay. So remember when we talked about the tangent line or the tangent plane, one of the conditions, again, was that our derivatives be continuous. And so one thing we might ask is, are these derivatives continuous? So these functions here that we're looking at are continuous everywhere except when there's a 0 in the denominator, which is when we have x and y equals 0. So they're continuous everywhere except at the origin. However, these are not the derivative at the origin. The derivative at the origins are just 0, right? So these would be continuous if the limit of these functions as we approach the origin was equal to the value. right? So these are just functions, and if the limit of this function, y, for instance, y cubed minus x squared y over x squared plus y squared squared, if the limit as x and y go to 0 is 0, then this would be continuous. These are tricky limits to take when we've got two variables. So we're going to do something a little bit, let's say tricky maybe. To simplify it a little bit, let's imagine, again, we're going to use a similar trick that we used before. Whatever our function looks like, right, when we're taking the limit, right, so here's the origin. I want to take the limit as x and y both go to 0, right? Going to 0, right, in one dimension, we have real valued functions. We have to look, remember our left and right-handed limits, we have to look from both directions. Well, it's a little trickier here because we have many directions from which we can approach 0, okay? And in order for the limit to be 0, it has to approach 0 from every direction, okay? So I'm going to approach 0 from along a particular path. I'm going to approach 0 along the path. So again, I'll just draw the xy plane in our normal orientation. Here's x and y. I'm going to approach, here's the origin, I'm going to approach along the line y equals x squared, right? So I'm putting in points like, you know, you can imagine putting in the point 2, 4, 1, 1, 1/2, 1/4, right? And so on and so forth, right? As we approach 0, letting both of them go to 0, but the condition that y is always equals to x squared. So it's like approaching it along, along a particular path, okay? So with that in mind, let's look at, for instance, f of x, xy, along this path where y equals x squared. So I'm going to take every y here, oh, I did different in my notes, but I think it should be all right. Hopefully we can work out the same algebra. We're going to look at the point along the path y equals x squared. So for every y, I'm going to put in an x squared. So I'll get y to the 6th minus x to the 4th over x squared plus x to the 4th squared. Oops, that one, first one should be an x to the 6th, right? So I'm just replacing all the y's in this function with an x squared, right? So I think I've got that right now. X to the 6th, we get another x squared here for x to the 4th. This one becomes x to the 4th. All right, let's do a little bit of algebra. Remember, my goal is to see what's the limit of this function as now x goes to 0, because that's also making y go to 0 because we're following this path to the origin. Just want to do a little bit of algebra. So the top can be written as x to the 4th times x squared minus 1. The bottom, I can factor out an x squared. I'll get x squared times 1 plus x squared. This whole thing is squared. I can distribute across these two factors the squared. So I end up with x to the 4th over x squared minus 1 over x to the 4th 1 plus x squared. This cancels, and I've got x squared minus 1. Oops, I forgot my squared here. Over 1 plus x squared squared. Okay, so along this path, the path where y is equal to x squared, maybe I'll write it this way, this is what my function looks like. And this is an easy limit to take as x approaches 0. The limit as x goes to 0, which remember includes pulling y to 0. It's along this path, so it's already baked in. This function exists at 0 that we've got now, and I can just plug 0 in and I get -1 over 1 or -1, which is not equal to 0, which is what we said was the condition on continuity at this point. So the limit as we approach 0 of the derivative, the x derivative is not 0. I don't even need to check the other one. It's going to work out the same. And you can come up with other paths and you'll get different values for the derivative. So it's very similar to what we saw when we were looking at the values of the function. The values of the function as we approach 0, we're jumping all over the place. The values of the derivative are going to be different along different paths. There's going to be these different slopes happening. And it's just this very confusing point for the function. So where does this all leave us? We'll go take a picture. We'll take a look at a picture of this in just a moment. This is also this condition to having a tangent plane. The idea that to have a tangent plane, you're going to also have to have continuous partial derivatives is exactly the condition on differentiability. So when we say a function is differentiable, there is a definition that's not as easy to check. It's something like delta z. A function is differentiable at the point a, b if delta z, the change in the function, is equal to the x derivative at a, b times the change in x plus the y derivative at a, b times the change in y, plus we have these two error functions that often use epsilon, whose limits have to go to 0. These have to go to 0 as delta x and delta y go to 0. This is not it's a really good definition. There's nothing wrong with it at all. I'm going to gloss over it for now. I don't think it's as useful for us. It essentially is saying that the tangent plane using the partial derivatives is a good approximation. If that's true, then these error functions, right? If you're not right at the point A, B, if you're a little bit off it, these error functions take care of the difference, but they shrink as you go to 0, right? What we saw in this case is depending on which line you're moving along, for instance, if your error function, if you're moving along the line y equals x, the difference between the tangent plane approximation and the function is always 1/2, and it's never changing as you go to 0. So these error functions aren't shrinking as you approach 0. They're staying the same. And so that's one of the issues with this function not being differentiable there. So it's not sufficient to just say we have partial derivatives. So this is the definition of differentiability, including all the words that I said, but I'm not writing down. But what's more useful for us is this definition is satisfied if, by the following theorem. We will say a function f of xy is differentiable at AB if the partial derivatives with respect to x and y exist and are continuous at AB. Okay, so this is different than in single variable calculus. We need this extra condition about continuity. And I just also want to say the notion of differentiability is now a little bit, before it just meant has a derivative, right? But it's a little different now, and what it really means is we have a linear approximation. Linear in 2 dimensions means a plane. We have a good approximation. That's really what differentiability is all about. It just so happens in single variable calculus that equates to having a derivative. But here's an example where both these derivatives exist, but we don't have a good approximation. And so differentiability is really about that approximation, right? So this is more the condition we're looking for what we might call well-behaved functions, that they have these good approximations at every point. All right, let's finish up by taking a quick look at the derivative function that we just computed. So here is our function. Let me zoom out again, kind of flatten it again. And here is the derivative function. And notice it has these spikes in different directions as we approach 0. Let's get rid of our original function. Let's zoom in a little bit. And this one's pretty hard to look at The computer has a bit of a hard time rendering it. But let's look at the cylinder y equals x squared, right? Approaching along that path that we were just looking at. Right, we saw that the value of our function, depending on where we were coming in at, had a value different than 0. We can see that intersection here, though it gets hidden behind some of the curve here. It's a little bit trickier to look at, but that's the notion, is that we're coming in along that path, and has quite a hard time rendering it here. So I don't know that this is as easy to look at and figure out what's happening here. In any event, that's the extent I'm going to discuss differentiability right now. We're typically not going to have functions that are going to try to trick us. The example was pretty hard. For most cases, they're going to be recognizably continuous, right? Things that, if we're looking at tangent planes in places where the denominators aren't 0, we don't have this kind of our typical misbehaving things, right? We know where those happen: zeros in denominators, square roots of negative numbers, things like that kind of screw up our functions. So this one, for instance, the clue that there might be a problem is that it's not defined at 0, 0. So that's a tricky spot and often leads to issues. For most of the stuff we look at, we won't have to worry so much about those things. Okay, that is it for this one. Thanks, everybody.